Uh, Welcome everybody to my talk entitled Statistical Representations for Fine-Grained Recognition. My name is Piotr Koniusz. I'm a senior research scientist at Data61 and an honorary senior lecturer at the Australian National University. So first I wanted to thank the organizers of this fine-grained recognition challenge for inviting me to give a talk. Today I have quite a dense agenda. So I'll talk about low sample problems that include fine-grained recognition. I'll talk about the statistics in a low sample regime. I'll talk about power normalizations and the relation to heat diffusion on graphs. So this is our recent work accepted to TIPAMI. I'm very excited. And finally, I'll talk about few-shot learning via second-order statistics and subspaces, few-shot action recognition. And we'll stop here today, probably because we will not have more time. Fine-grained recognition typically assumes that we have a number of classes which are seemingly very similar. It is difficult to recognize the objects belonging to fine-grained categories for untrained eye. And problems such as domain adaptation, zero-shot learning, one and few-shot learning very often work with such data sets. So it's not only the image recognition, but also other problems. And today I wanted to focus on image classification, one and few-shot learning, and also I will talk a little bit about graph classification in such a setting. So everything really starts with capturing robust statistics when it comes to computer vision. One can capture statistical moments from 0 to infinity, and that enables us to capture entire data distribution. Obviously, mean captures the first-order statistics, covariances capture second-order statistics, and then higher-order statistics can be captured with higher-order tensors. However, with a low number of samples, it is hard to obtain robust high-order statistics, which leads to poor estimates, which brings me to the notion of so-called burstiness. This is a property that a visual element appears more frequently or less than statistically expected, and it's a source of nuisance variability. So burstiness is a signal, but it is not useful for the purposes of classification. And this is a term coined by Hervé Jagot in 2009. However, the idea was explored actually way before in this ICIP 2005 paper, where feature vectors were square rooted before they were fed to the intersection kernel. To explain what power normalization does, I'll prepare a little illustration here. So assume that you're trying to distinguish the plant from the background, and you extract some foreground descriptors. Over here, you extract some background descriptors, and then you train SVM. At the same time, at the training time, maybe you have another image. You extract again foreground descriptors, background descriptors over here, which leads to statistics again, but now they differ from trained statistics, from training statistics, which means there's been a drift. And now SVM struggles to recognize correctly foreground from background. So this is obviously a problem. And one way around it would be to just detect across images some consistent representative patches, but this might be hard. So instead, it is easier to essentially equalize statistics via power normalization. And the form of power normalization is given by essentially raising features to the power of gamma between 0 and 1. Typically for square root, this is 0.5. Instead of selecting best patches, it is easier essentially to equalize the statistics that we capture. So here, just example, we extract descriptors from foreground, from background, we train SVM, and then for another image, we extract statistics from foreground, background, and thanks to the power normalizations, those statistics are very close to the training statistics. So now there is no drift, and we're able to recognize the plant correctly. So power normalization reduces so-called feature bursts. Of course, if we had infinite number of samples, and we would be able to observe all possible configurations of foregrounds, backgrounds, and different configurations of objects, we would not need perhaps this tool. But in reality, we have to work with finite data. So next, I'll explain this in the context of pooling. So imagine that we have some patches, X1, X2, and so on. Imagine that we pass them through some CNN network, or we extract local sieve descriptors. We obtain some nonlinear embeddings phi. We stack them, and then we essentially perform some pooling using function G along rows to obtain a signature of an image over here. So this can be performed in very simple 3 steps: encoding, pooling, and then we can have some normalization and classification. Most of practitioners in computer vision are familiar with average and maximum pooling. The difference being that average pooling performs the count of a given visual feature across some region. It is a normalized count, of course, and maximum pooling detects the presence or absence of a given visual word or some stimuli that responds to CNN filter. So the observation is the maximum pooling is invariant to repeatable visual stimuli. It doesn't matter how many patterns of the same kind is detected. As long as one is detected, this is the evidence. And analytical pooling operators built on that. So essentially, they are not maximum pooling, but they are statistically motivated operators. So-called max-exp operator, in fact, can be interpreted as a probability of at least one feature responding to some given stimuli to be one, given a visual word or CNN filter, or you name it. And simply follows the assumptions that if you draw features from Bernoulli IID according to IID principle, then you arrive at this very nice nonlinearity that corrects the average of a region. ExaPro computes probability of at least one feature present in an image as well, but it doesn't assume Bernoulli distribution. Power normalization, which is rising p to the power of gamma, can be shown to actually fulfill very similar role. And in our old work from 2013, we also proposed so-called top-K pooling with a universal pooling approximator, which is essentially a linear function clipped at 1. So it's got this type of non-linear profile, which is very similar to power normalization. And we showed that all those operators really are related. They perform a detection of features rather than counting, and they can deal to some degree with the non-IID assumption. To give you a better idea, this is a synthetic experiment. So assume that we have 1,000 regions drawn. Each is described by 10 features drawn from the uniform distribution, again under IID assumption. Then we order all the pooling responses by the response of average pooling from the lowest to the highest response. So you can see over here the response of maximum pooling, and it is clear the exapro is the upper bound of maximum pooling. And at the same time, this maxexp function over here is in fact lower bound of exapro. Why this is interesting is because maxexp essentially is a function that corrects average of features, so it can be very efficiently computed, and it has application in fine-grained recognition where one is not concerned with counting features but actually detecting some unique features correlating with maybe beak or some pattern on the wings and so on. Essentially, it's about picking up the needle from the haystack. But now I wanted to talk a little bit about capturing statistics, because capturing robust statistics is not only about capturing the mean of some feature vectors, but potentially capturing second-order statistics in form of matrices or higher-order statistics captured by tensors. So just to give you an idea, capturing third-order statistics can be performed by computing outer product of a vector with itself, vectorizing it, and then computing outer product with the same vector again. So that may be written perhaps as V times V transpose, and then of course times V again after vectorization. So we denote this outer product of higher order over here. And the reason why I'm talking about it is because it can be shown how those tensors interplay in capturing statistics. So imagine that you want to compare images or videos or text or whatever document you like. Assume that you want to capture distribution of patches or local descriptors, receptive, I don't know, response to CNN filters in a given image. The characteristic function can be written in this form over here, and it will describe the probability density f given patches X distributed according to some distribution big X. So that gives us the Taylor expansion of this form over here. Of course, this is expected value over the distribution, but in practice, we have a finite number of observations, so we can approximate it with finite sum of this form. And as you can see here, we have those outer products of order R that appear. After crunching a bit of mathematics, we arrive to an equation over here, which is a sum of orders of 0 to infinity between tensors of order R and this outer product of the frequency vectors. So higher order statistics can be captured with higher order tensors. They are more informative. So a third order tensor is supposed to be more informative than second order tensor. But also the number of elements in third order tensor grows cubically with respect to the size of feature vector. So this is a problem because it means that we cannot really estimate it very reliably. But to give you an idea of pipeline, just simply assume that you have some patches, X1, X2, and so on. You pass them through some CNN network to embed them in some higher dimensional space. You essentially have some nonlinear embedding. You obtain phi1, phi2, and so on. Then you perform this higher order outer product. You stack obtained tensors. And again, you perform some pooling with function G. So this can be performed in 5 steps over here. Encoding, outer product, vectorization, perhaps if you want to use it, pooling with some power normalization, and L2 normalization or not. And in our old work, seminal work from 2013, that was later on extended to TBAM in 2016, we showed that in fact third order pooling performed better than second order pooling, and applying power normalization brought about 10 to 20% gain by equalizing those two through occurrences of features. And now I wanted to explain a little bit what is the relation of power normalizations to non-linear distances, especially Riemannian distances. So for the Riemannian distances, one has to assume that we have some symmetric definite cone of the matrix. We can compute the tangent to the manifold. And of course, on the tangent, we are trying to compute the distance. Power normalization differs a little bit in the respect that, for instance, imagine that we have covariance V. We apply power normalization by raising V to the power of 0.4. That performs normalization of eigenvalues. If we apply power of 0.2, those eigenvalues are even further equalized up to the point where this covariance becomes isotropic. Second order statistics are not a new idea. In 2006, they were used, for instance, for detection and classification. Non-linear, well, not non-Euclidean distances like logarithm map were also applied before for semantic segmentation, for instance, in 2012. However, log Euclidean distances, they don't work with semi-definite matrices because the idea is that the point should lie on the manifold of positive definite matrices. So in terms of semi-definite matrices, log Euclidean distances yield infinity. Other distances following the Riemannian family are affine invariant Riemannian metric. And of course, there is a power Euclidean distance that was applied in 2009 to diffusion tensor imaging. But the relation between Riemannian distances and power Euclidean is perhaps a little bit vague. So for instance, in the limit where gamma tends to 0, power Euclidean distance is equal to log Euclidean distance. But in my opinion, it doesn't really matter because in fact, we never work with gamma equals 0. We work with gamma typically around 0.5. So in that regime, power Euclidean distance is not an approximation of log Euclidean distance. The only other non-Euclidean distances that are similar to power Euclidean are matrix square root and Cholesky, which work well with semi-definite matrices. If you're interested in this topic, we ran in 2019 an ICCV tutorial that discusses those aspects. So there are several talks. You're more than welcome to visit the link over here. Also, if you're interested in the huge number of papers that in one or another way perform second order pooling or bilinear pooling, there is also a web page here that lists all those papers, but I won't be going into those things today. Instead, I wanted to talk a little bit about our recent work focusing on taxonomy of power normalization. We studied different PN variants in scene classification, fine-grained image recognition, few-shot learning, and even graph classification to clean up a little bit the notion of power normalizations. And this is a recently accepted work on this topic in TPAMI 2020. So the pipeline that we use is very simple. We assume we have an image or patches. We pass them through some CNN. We obtain those embeddings into nonlinear space. We can even concatenate embeddings of the location of the patches, and then we apply out a product. We compute autocorrelation matrix, and now we can compute either a pooling that is element-wise. This is denoted by GI, or a GI hat, which is spectral pooling, and then we can pass it to the classifier. And in fact, there's a huge number of different variants of such operators, because firstly, they can compute power normalization element-wise, or they can compute it in spectral domain on eigenvalues. Then for the element-wise operators, some of them operate on non-negative elements, but we extended the notion of power normalization to positive-negative range. For the spectral operators, we extended it also not only to symmetric semi-definite matrices, but also to indefinite matrices, so-called crane spaces. And finally, we discovered a relation between power normalization covariances and heat diffusion process on graph Laplacians, and this is the key outcome of this work. So over here below, there's a list of various operators that we use, and it explains how they behave, how the derivative of those operators behaves when p tends to 0, what happens for positive, negative values, and so on. And over here below, we have also a list of spectral operators. So here, this is a standard power normalization where autocorrelation or covariance matrix is risen to the power of gamma, and it has a closed form derivative. I believe that it requires Sylvester equation to solve it, or one can compute it via SVD. There's our operator called maxexp, and it has a closed form derivative, which of course can be also computed by SVD. There are two other operators that work in the crane space. And finally, there is the heat diffusion process that operates on the precision matrix. And we are the first to show essentially relation between this operator and power norms. So just to quickly summarize, over here we have illustration of different pooling functions. We have gamma in blue, which operates on non-negative values. Then we have Arcus sine hyperbolic, which naturally extends it to negative values. We have maxexp, which again operates only on positive values. Then we have sigmoid, which extends it naturally to also negative values. And as you can see, maxexp essentially saturates at 1, while gamma doesn't. And also the derivative of gamma at 0 tends to infinity. But one of the interesting things that we studied was the relation between first order maxexp operator, which can be interpreted as the probability of of at least one feature occurrence event in some set of phi n vectors given n trials. So this is given by the nonlinearity over here. After crunching a bit of mathematics, it turns out that for second or higher order pooling, a probability of at least one co-occurrence event of feature phi n with some phi prime given n trials is given by exactly the same nonlinearity if we assume that those features are drawn from multinomial distribution. And the proof is perhaps a little bit more involved, but essentially after crunching the mathematics, one arrives at the same nonlinearity as for the first order pooling with max_exp. The reason why it is interesting is because it essentially explains why this nonlinearity can be applied to different order poolings. And I just wanted to know that many papers in CV computer vision use matrix square root, which is an approximation to this type of pooling. So root-sieved Fisher vectors, bilinear pooling, they all use square root normalizations, but they don't study the role in depth. But what we have observed is that actually that explains, for instance, the role of a sigmoid function in perceptron. So imagine that you have some signals x1 to xd, pointwise convolution with w1 to wd, and then essentially you have this nonlinearity which detects whether one of those signals correlated with W filter was detected or not. So I personally find it quite interesting because that explains the role of sigmoid in perceptrons. Now, I wanted to move to a explanation what is the relation between power normalizations, the spectral ones, and the heat diffusion. So if you look at the plot at the bottom, essentially we have the blue curve, which is the max_exp for some eta equal 10. Then we have the gamma pooling. This is the red curve. The minimum between those two is an upper bound of this function in beige over here, which is essentially the curve for the heat diffusion process. So to explain this, assume that we have a multivariate Gaussian distribution captured by covariance, denoted as M. With each M, we have associated the precision matrix Q, which corresponds to so-called loopy graph Laplacian. Just to simplify computations, assume that M is trace normalized, and the spectral max_exp is given by this function over here. You can also write the heat diffusion as exponentiation of the matrix Q with the reverse sign. Then in fact, for each eta, you can find such K that it will be a good approximation of max_exp. And essentially this is shown in this plot over here. So the further explanations of that mathematical derivations are in our paper, but this is quite an interesting relationship because that means that power normalizations are in fact heat diffusion. To illustrate that further, assume that we have some distribution of spectrum. It follows beta distribution over here. Now, if we pass it through our max_exp operator for sufficiently large eta, most of eigen values will concentrate around 1. Now, the same can be observed for gamma, for sufficiently small gamma. And in fact, the same can be observed for heat diffusion process for correctly chosen T. So as you see, most of eigen values will concentrate around 1. So we proposed an approximation of heat diffusion process, which follows those two functions. Time equal 1 means that we have our original matrix M. nothing has been done to its spectrum. Now, if we perform diffusion, of course, time moves forward. So we raise matrix M to some power of H. H is parameterization that depends on T. And if we want to reverse heat diffusion, for instance, to find a previous state, our max exp operator actually performs that. So for T less than 1, we obtain a reverse to the heat diffusion. And in our paper, we show that those two things are essentially very close to each other. Now, the important observation for end-to-end systems is that the spectral max exp has a closed form derivative, and it scales linearly with respect to parameter eta, which is good because it means we don't need a SVD to compute backprop. But actually, we have shown that max exp and its derivative scale sublinearly with respect to eta if we use exponentiation by squaring. So this is algorithm over here. This algorithm essentially utilizes the fact that matrix exponentiation can be computed using the tree structure. So it has the complexity that is log eta, which is sublinear. In practical runs, we have found that we require about 8 matrix multiplications per pass for eta equal 50, which is a typical value. And for instance, in the other methods in the literature use Newton-Schulz, which requires approximately 60 matrix multiplication. So that is quite few more, which costs extra computations. In backpropagation, again, we needed only 11 matrix multiplications, while Newton-Schulz needed around 120. And again, in terms of the memory, max exp is also a little bit more favorable compared to Newton-Schulz. So the papers that we compare ourselves to are those that use the matrix square root, for which the derivative can be computed with Newton-Schulz. This is an approximate derivative. So there were papers from BMVC 2017, from CVPR 2018. And also there exist many other papers that use SVD in one way or another to apply some form of power normalization. For instance, this paper from 2018. Just to give you an idea of the results on the fine-grained recognition over all data set flower 1 or 2, for spectral max exp, we obtain over 97%. Element-wise performed a little bit worse. Element-wise gamma even worse, and just bilinear operator was the worst performer. On FMD, again, just element-wise max exp outperform other methods. On MIT, element-wise max exp outperforms, for instance, the Fourier-based features. And on Food 101, which is a large-scale food fine-grained recognition data set, we, for instance, outperform kernel pooling. And in more detail, we also have comparison on graph classification on MUTAC proteins and CI1. We compared, for instance, the performance of max exp computed using the fast derivative, and it's better than computing derivative via SVD, which is not surprising because computing matrix multiplications is more numerically stable than using SVD. Then again, a heat diffusion process performed very similar to max exp. It requires backpropagation via SVD. However, spectral gamma and especially the matrix square root with neutron Schultz performed actually worse, between 1 and almost 4% compared to our method. And the reason for that is that a matrix square root just assumes gamma equal 0.5. Our method has this tunable parameter eta that can reduce the burstiness to desired level. And in terms of graphs, this parameter eta played crucial role, I believe. Even for gamma, the optimal parameter was an 0.5. Okay, so now I just wanted to very quickly talk a little bit about second order pooling paranormalization in few shot learning. We worked on this interesting pipeline where we have several support images, query in which we pass them via encoding network F. We form second order pooling descriptors. Then we concatenate descriptors of support image with the query. We apply power normalization. We pass it through similarity network. Without getting into the details of mathematics, we studied the reason why power normalization is useful in second order pooling. So in fact, we concluded that because few shot learning is in fact relational learning, it benefits from power normalization even more than regular classification. So this J along x-axis denotes the shot number. 0 means standard classification, 1 means one shot. And we showed that because power normalization reduces burstiness, in fact, it reduces the effect of reducing this burstiness is even more profound, as expressed by this function of kappa, when we have to compare two images against each other, or three, and so on, versus just performing regular classification. So if you're interested in that, the details are in one of our papers. Now, just to give you an idea of results again, few shot learning on flower 102. This is a 5-way, 1 shot, 5 shot. The max exp, again, a spectral version with fast computation of derivative outperformed the other operators, but only when the network is in fact pre-trained on, for instance, ImageNet. When the network was trained from scratch, in fact, just element-wise operators were better. On Food 101, again, we observed the same behavior, that when a few shot learning network was pre-trained, then the spectral operators were better. But if the network was trained from scratch, element-wise operators were better. And we performed the analysis of that, and we concluded that spectral max-exp, in fact, reduces diffusionness of the signal in the autocorrelation matrix. Therefore, if the network is already pre-trained, by reducing the diffusion, it means that some of the features are close to 0. They will not be updated, which means that spectral max-exp prevents, in fact, catastrophic forgetting by reducing some spurious correlations. And this is a very, very interesting observation, very interesting result in our opinion. So just to conclude, the second order pooling works really nicely, and the relation learning setup. We published a few papers that exploit second order pooling and power normalization, one in VAGV, one in CVPR 2019. We also have results on other data sets like OpenMIG dataset, which has exhibits of a fine-grained nature. that kind of shows that those pooling methods, higher order pooling methods, work really nicely with fine-grained data sets. And then, of course, we also tried second order pooling, or its equivalent, using subspaces to represent aggregate of images per class, rather than computing second order pooling on descriptors per image, which also worked very nicely. PSN obtained very good results, and this PSN plus is a variant where we push subspaces per class away from each other, which performed even better. We also tried this idea for few-shot action recognition. So we have a very simple pipeline where we have support clips, a query clip, we push them through C3D feature encoder. We obtained several feature blocks. We have temporal and spatial attention to highlight which of those blocks are important. And then we again apply pooling. We form second order descriptors and we push them to the relation network. And this is work published in CCV 2020. And what we've observed is that, of course, using temporal spatial attention, self-supervision, and making attention invariant to permutation of blocks improves results over baselines. But also we observed that using second order pooling with paranormalization outperforms first order pooling variants. We apply this idea also to the few-shot object detection, where we have a support images, query image, we pass them through encoding network, we apply second-order pooling, we use hyperattention network to find the related regions between support and query, and we feed those to similarity network. And again, for second-order pooling, we obtained significant improvements over state-of-the-art. Over here, we also compared few different second-order pooling variants versus first-order pooling, which obtained better results. So this concludes the talk. I just wanted to thank my PhD students who worked with me on all those problems, and I wanted to thank my collaborators, Dr. Harandi, Richard Nock, Fatih Porikli, and many, many, many other amazing people. So thank you very much.